Hello, here's a few more magnetic fields questions. We start with figure 3.1 shows the variation of the magnetic flux linkage with time for a small generator. Generator's got a flat coil, negligible resistance, rotated at a steady frequency in a uniform magnetic field. They've given us a number of turns on the coil, the cross-sectional area of the coil. Then the output of the generator is connected to a resistor of resistance 150 ohms. Right, calculate using the graph the frequency of rotation of the coil. So it's taken us from, there's one maximum, there's the next maximum. So that is 10 times 10 to the minus 3. Don't forget your the multiplier on the axis there. So our period is 10 times 10 to the minus 3, which is 10 to the minus 2 seconds. So our frequency, which is 1 over the period, is then going to be 100 hertz. Then we need to calculate the magnetic flux density, if I can say it. Calculate the magnetic flux density B of the magnetic field. Right, so what's our chain of stuff that we've got in magnetic fields? We start with our magnetic flux density. Then we go to magnetic flux, which is then the magnetic flux density through a particular surface. So remember, this is our BA cos theta, depending on where you're taking your angle, but usually people go cos theta. Now we can ignore the cos theta if the area, as in the surface, and the magnetic field are perpendicular to each other. And that's where we're going to get maximum flux linkage. So if we've got maximum magnetic flux linkage, that's going to be equal to B times A times N, because our magnetic flux linkage is the magnetic flux multiplied by the number of turns. So that means we're just ignoring that cos theta because that's going to be equal to 1. Obviously, you don't need to put all of this bit in your exam answer. We're just doing that. So what is our maximum magnetic flux linkage? It is 2 times 10 to the minus 2 Weber turns, and that is equal to B times 1.6 times 10 to the minus 3, and then number of turns is 400. So let's get rid of some of these. So we can get rid of, what have we got on all of these? 10 to the minus 2 off of there, leave that as a 10 to the minus 1, which we can cancel with that 0 off the 400. So B is going to be equal to 2 divided by 1.6 times 40. 2 over 40 is 5 times 10 to the minus 2, and then divide by the 1.6. How many 1.6s into 5? 3 of them give us 4.8, and then we need 0.2, which is an eighth of 1.6. So we're going to have 3.125 times 10 to the minus 2 Tesla. So we want to say, well, 3.1 times 10 to the minus 2 Tesla to two significant figures. Right, show that the maximum electromotive force induced in the coil is about 12 volts. Right, so we're going to get a maximum EMF induced when we've got our maximum rate of change of magnetic flux linkage. So that's where we're going to have the steepest gradient, which is always a nightmare doing this on a screen because we need to take a gradient when it's changing quickest. So let's go to this point here where it's cutting through 0. This is where it's cutting the x-axis at 7.5 times 10 to the minus 3. Then we're going to need to take a gradient off of this. Now this is a nightmare on here, like I say, but you're going to have something like that. Right, I'm going to have to do, oh right, they seem to have given us some fairly okay numbers. Right, so let's go on that and that. So our change in y is, what's it going from 3 to minus 3? So that is 6 times 10 to the minus 2, divided by our change in x, which is going 5 to 10 times 10 to the minus 3. So 5 times 10 to the minus 3. So that is 6 over 5, 1.2 times 10. Oops, I'll put out the change in x. But anyway, so 1.2 times 10 is 12 volts. Right, okay, that was a very friendly gradient to draw on there. Right, hence calculate maximum power dissipated in the resistor. So P max is going to be equal to V squared over R. So 144 over 150. So what's that then? That is 72 over 75. So add a third of 72 on to give 96 over 100. Right. So that is 0.96 watts. Right, is that the whole question? It is indeed. Right. So that's the first question down. Define electromotive force. Right. We've done this loads in these videos. So again, we're starting off. These are volts. So start with your definition of the volt, energy per unit charge, then transferred from the source to electrical energy. All right, so I'm not writing that out. Done it too many times before. Define magnetic flux. All right, again, we've done this quite a lot. Contextualize the magnetic flux as we did, I was saying this on the previous question. This is magnetic flux through a surface. So start off by saying that the magnetic flux through a surface is the magnetic flux density perpendicular to that surface multiplied by the surface area. So contextualize where you can. Yeah, we could have done the same with the EMF. You could have said the EMF of a source, of an energy source, you know, so that you can then use that word source later in the sentence. Right, so anyway, that's our two definitions. We've done those quite a few times before. Figure 1.1 shows a simple transformer. Right, so this is a step down because we've got fewer turns on the secondary coil. Primary coil is connected to an alternating voltage supply. Explain how an EMF is induced in the secondary coil. Right, the key for these on exam questions is not to get too bogged down. Just keep it simple in the explanation. They're not expecting for degree level explanations around inducing EMFs. So let's say three things on this. We can say that we want to say that there's a changing magnetic flux produced inside the primary coil. Changing magnetic flux produced inside primary coil. Right, so that's the first thing that we've got. Yeah, we know that this is true inside primary coil. Then what does that do? Right, we can then say that we need to say something about the iron core. So the iron core links this flux to the secondary coil. So this is where people can get really sort of bogged down in trying, get confused as to what it is they should say. But don't make it too complicated. They're really not looking for a lot in these mark schemes. We're just saying that the role of the core is to link the flux from one coil to the other coil. So leave it at that. Then we can say that the sort of, similar to the first one, that the changing magnetic flux linked to the secondary coil induces an EMF. So, I mean, I know it sort of, it leaves things hanging a little bit about exactly what's going on here, but, we're not doing a degree yet, so let's not get carried away. At least we can see what the general process is at high level, and if we're doing more physics, we can then pick this apart as we get more skilled in our descriptions. Right, state how you could change the transformer to increase the maximum EMF induced in the secondary coil. Right, okay, so, well, we want more coils on the secondary or fewer coils on the primary. But let's say more coils on the secondary. So second part here, so more coil, more turns on secondary coil. On secondary coil. Because remember that our induced EMF that we're going to get in this secondary coil, of course, this is proportional to the rate of change of flux linkage. So and we know that our flux linkage is going to be alternating, in step with the alternating current. So the greater the maximum flux linkage we can produce in the secondary coil, the greater the induced EMF. And we know that our flux linkage is proportional to the number of turns on the coil. So, you know, the more turns we've got, the more flux linkage we've got. So, you know, we know that that is the case for our induced EMF. Right, so yeah, more turns on the secondary coil. Of course, you could have fewer turns on the primary coil. That's another thing that we could do. Anyway, but I've gone for more turns on the secondary. That's fine. Right, a transformer with 4,200 turns in the primary coil is connected to 230 volts main supply. EMF across the output is 12 volts. Assume is 100% efficient. Calculate the number of turns. So we know that 4,200, the ratio of the number of turns to the voltage, is going to be the same on both of the coils. So we've got some number there to 12. So we just need to turn these into fractions and then solve. So we could say then, based on this, because we can just turn these into straight fractions, and then say that n is going to be equal to 4,200 multiplied by 12 divided by 230. So let's cancel that and that. Multiply 420 by 12, which is going to be 5,040, and then divide by 23. So it's not going to be an integer number of turns because that does not divide by 23. So 223s is going to give us 4,600. If we had another 20, that would be slightly over. So 220 is too much, 219 is too little, because that would be 5037. So we need 219 to 220 turns in order to get that output voltage, right? Because you don't have to have complete turns, you know, it's not a case of we have to go all the way round every time, so that's fine. I mean, I suppose we could stick it into the calculator, and it's going to be 219 and 3/23 is what we're going to have for the actual number of turns. But yeah, by the time we've made that two significant figures, we're going to say 220 turns to two significant figures. Well, what am I doing anyway? The transformer output terminals are connected to a lamp using leads that have a total resistance of 0.35 ohms. PD across the lamp is 11.8 volts. Calculate the current in the leads connected to the lamp. So our current is going to be equal to V over R. Well, the PD across the leads is going to be 12 minus 11.8. So we're going to have 0.2 volts left across the leads divided by 0.35. So that is 4/7 of an amp. 4/7 is about 0.57, isn't it? 0.57 amps, the two significant figures. And the power dissipated in the leads. So the power is I squared R. So that is going to be 4/7. So, well, 4 squared over 7 squared multiplied by, well, 35 that's 7/20. So we can cancel a couple of the 7s. So that's going to be 16/140. 4/35 watts. Well, I am going to put that into the calculator. 0.114, so 0.11 watts. Two significant figures. Right, okay, that's probably the end of that question, I would imagine. And it is, right, I think this is the last one. Pretty sure I had 3 on this. Figure 5.1 shows a rigid straight metal rod XY placed perpendicular to a magnetic field. Okay, magnetic field is produced by these two magnets placed on a U-shaped steel core, which is sitting on a digital balance. Weight of the steel core is as shown on the scales. Rod is clamped to X and Y. Rod is connected to a battery. Rod is clamped at points X and Y. Okay. Clamped to, okay, right, okay, I'm not too sure what it's clamped to, but anyway, it probably doesn't matter. The rod is connected to a battery, switch and ammeter shown in the picture. Direction of magnetic field, yeah, is shown. Switch is closed. State the direction of the force that now acts on the rod due to the magnetic field. Right, so I'm going to go with the right hand slap rule. So fingers, so you've got flat hand, fingers in the direction of magnetic field, thumb in direction of current. So that's conventional current, so that's going to be going that way through there from positive to negative. So we've got field lines as fingers, thumb as current, so slap is force, which is going to be downwards. So that's going downwards. I mean, you can do Fleming. Oh, they're saying here, part B, state how you determine the direction of the force. So I'm going to lie and say that it's Fleming's left hand rule. Of course, you could use Fleming's for this. As I've said in previous videos, I'm not a big fan of Fleming's rule. It just seems more contortion is required. Part C, the length of the rod in the magnetic field is that long. Current is 4 amps. Assume that the magnets provide uniform magnetic flux density of 0.08 Tesla. Calculate the force acting on the rod due to the magnetic field. Right, so it's all perpendicular, so the force is BIL. So we've got, what was B? 0.08. We've got I is 4, pretty hefty current going through it. And then the length is 5 times 10 to the minus 2. Okay, right, so we've got 20 times 10 to the minus 2, so that's 0.2. So we're going to have 1.6 times 10 to the minus 2 newtons all in all. So yeah, 0.016 newtons. And we've got all of that put together. Right, okay, that's fine. State and explain the new reading on the balance. Right, so if we've got the magnet on this U-shaped steel core is pushing the wire, the metal rod down, then Newton's third law tells us we must have an equal and opposite force pushing up on the magnets. So Newton's third law means we've got force equal to 0.016 upwards on magnets or U-shaped core. So therefore our scales will read, what have we got, 2.5, that's an equal 2.5 minus 0.016, which is 2.484 newtons. Okay, that's fine. Then part D, last bit, the rod is replaced by another rod of the same material having half the diameter of the first wire and the same length. Potential difference across the rod is the same. Calculate the force on this rod due to the magnetic field. Right, so our if we've made that half the diameter, so what's going to happen with our resistance? So resistance is resistivity times length over area. We've not changed the resistivity or the length. So therefore our resistance will be multiplied by, well, let's start with the area actually. So we're saying here, let's put in here first, the area is multiplied by a quarter because we've halved the diameter. So the cross-sectional area is going to be a quarter. So our resistance is going to be 4 times bigger, which means that our current is going to be a quarter, which means that our force is going to be times a quarter because it's this, BIL, and we haven't changed B or L, we've just reduced the current down. So the force is going to be a quarter. So we're going to have the new force is going to be equal to 0.016 multiplied by a quarter, which is equal to 0.004 newtons. Yeah. Well, that's wrapped up that one. Over a couple of nice, that was a nice bunch all round, really. Covered a lot of different areas, although none of them were epically difficult, but yeah, it covered a lot of different bits, which was nice.